NeoBay Robotics Forum is an academic platform launched by Science Robotics in collaboration with the Institute of Medical Robotics, Shanghai Jiao Tong University, aiming to promote the latest advances in robotics and allied technologies, as well as ongoing basic science research and engineering challenges. The online forum is open to the general public and held monthly with speakers from leading research organizations and industries around the world.
To present our work here on enzyme nanobots, how we can make them going from in vitro to in vivo, and how do we actually mimic what you see here, like virus or bacteria model systems, right, at the micro nanoscale. How can we then make them swarm, like flock and fishes and swarms, right, and swimming entities, and all of that doing using artificial nanoparticles, but combining with enzymes. So that's why we call them hybrid. So what do we want to do? We want to change this paradigm, right? We want to go from the nanomedicine, the typical nanoparticles, to the nanorobotics for cancer theranostics. And the reason why we're doing this is because over the last years, there have been a lot of research done in nanoparticles, right? But a recent report says that only 0.7% of these nanoparticles designed to treat tumor, they reach to the target, right? So we want to do something different. We want to change the structure of this idea and go provide our solution, which is nanorobots, right? So it's self-propelled nanoparticles. Today, my talk will be divided in three main concepts. The first one is at the individual level. How do we get motion? How do particles interact with each other and we can guide them collectively? And how do we get this collective motion into something useful? Okay, so the first part of my talk, as I said, is to ask ourselves and to rational design something that moves. So how do we get motion at this scale? So this will be part A, part one. So, and then we need to learn again from nature. Nature has created very impressive examples like bacteria. They can move at the nanoscale, even though there's lower numbers where the viscosity is very high and there's no inertia, but they can convert chemistry through catalysis into motion. So we use enzymes. Why enzymes? Because these are biocompatible, but bioavailable, and you can find inside your body. So if you say, oh, Samuel, so which systems can you work on, and where can you use your system? Will be, okay, tell me what the substrate is there, and I'm sure we'll find an enzyme, because we have thousands of enzymes in our body which catalyze specific substrates. And just you need to code the particles and generate this chemical gradient around. Now, how to guide them? This will be the second part, right? So we look back into nature again. Living cells orient themselves towards organ gradients. That's called chemotaxis, right? Bacteria interact with surfaces. The sperm move against flows, or magnetotactic bacteria orient themselves with magnetic field. So why not to study these four different phenomena, right, in our system? I'm not going to talk about chemotaxis. There's a lot of controversy here, whether a particle can chemotax or no. We try ourselves, we reported ourselves like 10 years ago. Still, there's a lot, but that will be extremely beneficial, right? Because if they can follow the gradients, that would be really great. Now, what we have seen is that if you add some magnetic material here, that was a long time ago story, then you can control with the external magnet, right? Or if you have also this urease powered nanoparticle, we published a few years ago, you can also now, by placing the magnet, you can steer them, you can keep the persistent length of the particle and then turn them wherever you want. And we discovered, and then a few years ago, that if you have a big particle with a very, very small edge here, it's like tens of times smaller than the particle itself. The theory was done by all these people, all my collaborators from MPI Intelligent Systems, where the particle will come near the wall, they will just bounce against the wall, they will interact with it. It's not only hydrodynamics, but also a phoretic interaction. As you can see here, this is the product of the reaction. The oxygen will interact with the wall, and then the particles will align. And then we use this later on to make something which I think is very cool, to have a maze in microfluidics. And then by this ratchet-like structure, we put a bath of particles, and then the particles will rotate clockwise or counterclockwise without us doing anything at all. So the last part is, how can we go from a few particles too many, right? And this part of my ERC consolidated grant, what we call I nanoswarm, so as to go from the single particle motion you have seen right now to collectively. Why we want to do that? Because nature is collective by itself, right? So we have this collective intelligence in many systems. And again, this is what you can see here. What is the downside of these systems, of these thousands of particles moving collectively? That we don't have fully control, we don't understand this yet, and we know how to guide them, right? But you will see now the benefits. But the point is that we can put them, and they move in 3D, we can put them in vivo. So what we have in our lab is this multifunctional nanobot, which is patented, where we have different components. You can have the enzyme, you can have PEG linkers, DNA, antibodies, drug, nanoparticles, and for imaging and diagnostic and propulsion. Now, in the last few minutes, I will like to focus more on, okay, we demonstrated all that in vitro, then can we do it in vivo? Right? Can we use this for nanomedicine cancer therapy? And just one slide about our last work on skin bones. We injected intravesical because we want to go only to the bladder. So this is very nice because it's typical method they use in the clinic. They empty the bladder, they inject the drug, or in this case, the nanobot, they accumulate there. And once you start having the urine inside, this will be case number 1, nanomotors that you will see here. You see the red cloud, this PET-CT imaging, PET imaging of these nanobots reaching the whole volume. And this is the CT reconstruction. The red is the area that is touched by the enzyme nanomotors. And then the other case is all the other controls where there's no urea or there's no enzyme, right? They just sediment. And this is the problem they have in the clinic, okay? So the drug sediment, and they need actually to rotate the patient in order to the drug to reach the whole volume of the bladder. That's why the method is so inefficient. But with this case, we'll have a very efficient method and very fast.
But one of the key questions is to fulfill the fantastic voyage vision. How can we realize future, nano vehicle? How can we power future nano vehicles? So the object propulsion and nanoscale is quite challenging because of the low Reynolds number fluid. According to, if you learn the fluid mechanics, you may be familiar with Navier-Stokes equation. If you don't, which is fine also. When the Reynolds number is very small, actually it means the initial force is negligible compared to viscous force. In this case, viscous force dominates. How does this mean? It means to understand how this nano-organisms swim in water, we could have imagined how ourselves swimming in a pool of honey. It's very viscous, very hard to move. That's why the swimming strategy used in a larger scale world may not be applicable at nanoscale. So over the years, we have developed, and many other scientists in the world have developed micro nanoscale object or robots that can be powered by different mechanisms, including use local chemical field, use magnetic field, use acoustic propulsion, or biological hybrid propulsion, as Samuel also mentioned. So if we develop this nano vehicle that can be powered by a certain mechanism, we can also incorporate a different functionality. For example, we can immobilize the surface of this nano vehicle with different bioreceptors, including DNA, aptamer, antibody, and this type of functionalized nanorobot can recognize the target. I was still a PhD student. My first work thought about, can we design some artificial flagella that can mimic the nature bacteria flagella? In this case, we can design some flexible micro nanostructure that can deform under certain under microscope scale in general. So we can mimic, in this case, how E. coli swim, for example. So initially, I proposed a nanowire. We can design this bi-segment nanowire. The head is nickel, the silver is the tail. On the rotating magnetic field, the head will rotate. As a result, the tail will also follow. And the tail also design chemical powered micro nanorobot. In this case, we need to break the system symmetry by introducing asymmetric chemical reactions. So many people propose in platinum-coated dense particle, basically sphere particle, platinum-coated one side. We also use iridium-coated particle. For example, iridium can catalyze the decomposition of hydrogen. And this chemical reaction can generate a product gradient and also there are two different mechanisms for local chemical reaction powered nanoswimmer. One is the electrophoresis, and another one is diffusive phoresis. In general, the chemical fields which are not biocompatible, they have to be able to move in a salt-rich environment. In this regard, we propose another mechanism using microbubbles to power this micro nano robot. In this case, we propose using a polymerization approach, a template electrodeposition approach. By using this polycarbonate membrane template, we can deposit this bilayer structure. The outer layer is a polymeric shell, could be polyaniline, could be polypyrrole. The inner layer is platinum. Platinum can catalyze the hydrogen peroxide decomposition, generate oxygen bubble. In this case, if we have a tubular structure, one side is bigger, one side is small, in case of opening, the bubbles can inject from bigger opening and propel the micro robot to go the other direction. So in this case, we can design this micro bubble powered micro engine. We can also control this moving direction using external magnetic field. They can move very well in a different type of biological medium. Can move very well, but what can they do, right? We can immobilize the surface of this micro robot with different bioreceptors. As I mentioned from the beginning, this could be a DNA receptor, aptamer, antibody, or lectin. They can bond selectively different type of target. They can recognize which are bacteria, which are the cancer cells, and how to capture them and isolate them. To give you one example, we can modify the surface of this micro engine with lectin. Lectin is a sugar bonding protein. They can bond to mannose. So many bacteria, such as E. coli, has this sugar compound on the surface. That's why the lectin immobilized microengine can recognize the bacteria, E. coli. So we have a video here. This micro robot can contact with some cell, yeast cell, for example. The surface doesn't really contain that much sugar. Which kind of body fluid we can use to power micro robot? We're thinking about how about instead of platinum, we use some metals, some biocompatible metals such as zinc. Zinc, as we know, learn from high school chemistry, they can react with acid to form hydrogen bubble. So in this case, we designed this hydrogen bubble propelled zinc-based micro robot. And zinc is fully biocompatible and biodegradable, which is very helpful for in vivo application. That's why instead of platinum inner layer, using the same template electrodeposition method, we designed this bilayer structure with zinc as inner layer. So they can react with gastric acid very efficiently and to form this hydrogen bubble propelled micro robot. Joined Caltech, and we have developed an imaging guided micro robotic system. In this case, we still use our magnesium-based micro robot for intestinal application. And to protect the magnesium, go through the stomach, because we don't want this micro robot to get consumed in the stomach, right? That's why we also want to use imaging to locate the micro robot. One single particle may be too small to be see clearly, right? That's why we encapsulate the multiple certain number of micro robot into one capsule, and this capsule is based on gelatin. They can also protect this magnesium particle from the harsh stomach environment. And moreover, this relatively larger size allow us to directly visualize where are these type of micro robots. So we call this larger one like a micro model capsule, MC here. And using photoacoustic imaging, we can locate where are these capsules. We can see they enter stomach, go through stomach, enter intestine, which part of intestine it is. And when they reach the disease area, we can activate this type of microcapsule. We can release the micro robot at the disease area. In this case, micro robot can be powered by intestinal fluid. They can penetrate the mucus, they stay at a disease area for a longer time to realize sustainable drug release.